I have to repeat some formula because I'm jumping now to an old problem. Yes. First about the equations of equilibrium, because that's what we have to solve now. Your job will be start with the equilibrium and then find the oscillations. Okay. Equilibrium equations are lambda x is equal to lambda n plus 1 L lambda y is equal to minus mu, and lambda z is equal to 0, which you know this 0 can be forgotten because this means that 0 is, z is equal to 0. So the whole problem is plain. The only thing we have to do in the full space is to check the positive definiteness and the total global minimum. Once we have it, we can forget about z. Mu is a vector which has to do with masses. Yeah. That's what it is. And we know that the matrix lambda is positive definite. At the equilibrium. That's what we know. Because these, right. Then, by introducing the differences, we can write down those equations like lambda I 1 plus 1 Ci plus 1 is equal to lambda I Ci and lambda I plus 1 Ci plus 1 eta equals to lambda I eta I plus mu I. And we know that we have psi I squared plus eta I squared equals to di squared. And those conditions here now give some conditions for lambda for Xi. That means that the sum of all of all xi's equals to L. The xi, xi2, xi4, xi5 together give L. And for y's we have 0. For etas, excuse me. So, that's what we have. Now, those two equations can be squeezed into a single difference equation. What this means? That means that those products, lambda I, xi, are independent of I. It's a number. So, I can now divide this equation by this. That means lambda I plus 1, eta I plus 1 over lambda I plus 1, psi I plus 1 equals to lambda I psi eta I over lambda I psi I plus mu I over lambda I psi I. See, this is the same number, this and this. I can divide it. Now I can cancel this one, and I get then eta 1I plus 1 psi I plus 1 minus eta I or psi I equals to mu I over lambda I psi I. And this now can be further computed using this. This is equal to mu I over L times k is equal to 1 to n plus 1, 1 over lambda k. I will take the special case where all psi I are positive. When this will be the case? We know that's the case where each of those lengths are less than the total one. This is a special case. Will be true if di less than L for every I. And then we also know that all lambdas are positive, even then. Lambdas are positive. I just repeat what we have established last time. Now my next assumption will be that I have an odd number of points. N is equal to 2p minus 1. I will show you after that this is not a real restriction. So now I start with this equation and use this assumption. Now, I use now the symmetry. I look for the solution of these equations which has the symmetry. That means, what means the symmetry for xi's and etas? Well, we look for such ones that eta 1 is equal to eta n plus 1, and so on, and also psi 1 is equal to eta n plus, psi n plus 1, and so on. So now, it's not quite symmetric, but that's the symmetry axis here. If now I take here I equal to P, that means this is 1, 2, 3, P is equal to P is equal to 2 in this case. Mm-hmm. So what now happened? Now I have two equations from this same point, one from the left, one from the right. So let's write once more. Eta I plus 1. So P is equal, I is equal to P. Now I have I, which is eta P plus 1, or psi P plus 1 is equal minus eta eta P psi P equals to equals to no, that's not the symmetry. This is symmetry. That was my error. Symmetry means changing the sense of the differences. Okay? So now, this is now equal to mu I, mu P over nu, where nu is this constant here, which we know is independent of I, and this is a quantity which has to be determined. It's unknown. But now this is just twice the same thing, because those two lie symmetrically to each other and have different signs. So this is then just 2 eta P equals to mu p over nu. So we have the quotient of them, and we know that psi p squared plus eta p squared is equal to dp squared. We have two equations for two variables which we can solve. So now we can write down, solve this equation, giving us Ci is equal to Vi over square root 1 plus eta I, excuse me, eta I square or Xi I square, and this is equal to Vi over oh. So once you know this, then you go summing up all others, left and right. Because now the difference here for other i's gives you the possibility to compute the other quotients, left and right. So doing that, we get then equals to dE over 1 over 1 plus sigma I n over nu square, where sigma I is equal to mu 1 plus mu p minus 1 plus mu p square, half. You just add up. But now use that sum over xi's gives to L. And then you get something nice. You get d1 over 1 over 1 plus sigma 1 square over nu plus dp one plus sigma p square over nu square equals to L. Moment. L half, because you sum up only of the half of the catenary, the other is the same. Now, what we get here, what's that? What is known, what is unknown here? There is only one unknown, and that's nu. Everything is eliminated. This is the only variable which has to be found. Now, we know that we have to look for nu larger than 0. That's where we have to solve, because the product of lambda I and psi I, both of them are positive. And you have to, now this function is, as nu is yes, it is increasing, strictly increasing with nu. Oh, is it? Oh, well, it is. That's the point. You have the inverse twice, so it's increasing. And it has only one solution, which you can find numerically easily by bisection. If you are a bit clever, then you can a bit squeeze your interval of search. It is not just from 0 to infinity. You check this function at some points, and you will see that it changes. That it's changed. The difference changed the sign. So you can very finely find the solution. So what we did here, we solved completely our problem by reducing it to a single nonlinear equation. It is completely parallel, if you remember, to our case with two springs, which also was reduced to a single equation of a single equation with a single variable. So we found a symmetric solution which has a symmetry, and we know that getting now psi I and eta I is trivial. Eta I is the same eta I will be positive from 1 to p and negative from p to n. But it's easy, it's sufficient to compute only this part. So they will be then positive. So, now you can find now very precisely your equilibrium point to working precision of a machine. And then you can start oscillating. And that will be your exercise. Find small oscillations of this, of exactly this catenary with 3 points. Exercise. 3 points. Symmetric. That is, I will take these to be equal to 1. And we have 1, 2, 3, 4. D1 equals to D4 equals to, well, 1/2, and D2 equals to D3 equals to, say, 0.2. Equal masses. So now the exercise, the data are fixed. You don't need the concept of gravity for that. Why? Because it's independent of it. But check what I said now, check it. Okay. So this will now end up our considerations of moving systems with constraints. Next time we will once more concentrate on finding optima or finding examples other than mechanics which lead to minimizations which are relevant in applications, and that's, I can tell you, that will be given under the title LS or NLS, meaning least squares or nonlinear this will give you some other insight in this fascinating problem of optimization. I think 90% of jobs which mathematicians have somewhere else are optimize. Optimize, optimize, optimize till you die. And it's nonetheless interesting and nonetheless challenging because the optimization problems have so many facets, so many different aspects. Take, for example, the simplest case, E A to A B T is a function of two variables, variable t and parameters a and b. And you've got some points, t1, y1, tn, yn. And you would like to find a and b to fit these data with this function as good as possible. That would be mean sum up ti minus yi square equal to minimum. That's a typical problem. Now, with this special function, there are still a bunch of works doing now with it, how to do it efficiently. The most simple case, which is nonlinear, of course. Of course, in two variables, you can always minimizing just by plot. You in two variables can plot your function and look what happens. And but as soon as you get one variable more, then you will not able to make any pictures anymore. And that's what will be our subject next time. And then we will consecrate our attention to something quite differently. And that will be the problem of CT. You know what CT is? There is a big tunnel and you lie here and then you're put in the tunnel and then you hear something like boo, 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 boo. And then after you got some pictures about your bones, about your stomach or something like that. It is computed tomography. that will end up our circle of teams. Well, I'm rather done up, and I will break here.